today I want to go over 3 topics here. First, I'm going to focus on reviewing some theorems that you're going to be expected to see on the exam. So EVT, Rolle's mean value theorem. And then I'll review through those theorems. I'll also do an example of each. Next up, we'll do a particle motion problem, just practicing from position, finding velocity, finding acceleration, creating sign lines, determining increase, decrease, speed, and velocity. And then we'll do a problem where we have to work our way down to the second derivative function and determine intervals of concave up, concave down. Okay, so that's our concepts for today. So let's start off by reviewing extreme value theorem. Okay, so I'm just going to kind of go through each concept one by one. First up is extreme value theorem. The purpose of extreme value theorem is to find the absolute max and absolute min on the closed interval. Okay. The first thing we need to establish is that the function is continuous on the closed interval. So make sure that there are no holes, that there are no asymptotes on the closed interval. It's okay if there are holes and asymptotes as long as it doesn't impact the interval. So no holes, no vertical asymptotes on the interval. And usually that's just going to be in the denominator. So if you see any denominator within your function, that's a red flag that you got to pay attention and look to see if those locations of asymptotes or holes are going to impact our interval. So here's a diagram to kind of show you where the candidates for max and mins can come from. So the candidates are going to come from endpoints, and you're going to come from critical points. So your endpoints could end up being the highest and lowest points on the graph. So we want to make sure that that we consider those endpoints, that we are testing those endpoints. The next possibility is coming from critical points. So critical points is coming from the derivative. So the way we find critical points is we find the derivative first, and then we set the numerator of the derivative equal to 0 and the denominator of the derivative equal to 0 and look for those locations. So numerator of f prime equal to 0 is going to tell you locations where you have a smooth transition, right? The slope is 0, either a peak or valley, max or min. But we also don't want to forget about the denominator, because when you set the denominator of the derivative equal to 0, you're looking for slope undefined, and slope undefined is also a candidate. As you can see here, right, for this example, my absolute min is a location where the slope is undefined. If I never consider the denominator of the derivative for this graph, then I would have missed out on the absolute minimum. But by and large, we don't see a lot of instances with denominator of f prime with the denominator that exists. So usually this doesn't happen. Usually we're just looking in the numerator, or there's no denominator where we just set the entire derivative equal to 0 and we just find those slope zeros. And then after we do that, after we find our endpoints and critical points, we're going to plug into, that's our third step here. Okay, we're going to test endpoints and critical points into the function. And when we do that, we're going to get a series of y values, and we compare those y values, right? Highest y value is your absolute max, lowest y value is your absolute min. Okay, so here's an example that we'll try. Finding absolute max and absolute min for our function. 3x squared minus 6x from 0 to 3. Okay, so the first thing I notice is I got a nice polynomial here, no vertical asymptotes, no holes. I know my condition is good to go. Second thing I notice is I have 2 endpoints, so I definitely need to be considering those endpoints when I reach the end and want to test for max and mins. So then let's identify some critical points. So critical points is going to come from f prime, so we're going to take the time to find the derivative, set the derivative equal to 0, and look for critical points. So we find the derivative, 3x squared minus 6x. We go through power rule. We get 6x minus 6 equals 0. Solve for x. Okay, there's my derivative. I set that derivative equal to 0, factor out the 6, and I get x equals 1. So what do we have to be careful about with the critical point here? Where does this critical point have to live in order for us to use it? Yeah, between the interval, right? In this case, we're safe, but just to remind you that we can't just blindly test every critical point we come across. We always have to compare it against the interval. So it's possible that you may end up with a bunch of critical points and none of those critical points fall inside the interval. If that's the case, then you're only testing your endpoints, right? We don't have to have a candidate for critical points, but we just have to look for it. But in this case, it looks like 1 falls nicely inside the interval, so we're going to have 3 points to test. We have 2 endpoints and 1 critical point. And now we're ready for the third step. We're going to plug each of those x values into the original function. And the result that we get, we're going to determine which is the absolute max and which is the absolute min. Okay, so we'll find f of 0, we'll find f of 1, we'll find f of 3. So if I plug 0 in for x, I get 0 minus 0, which is 0. Okay, I plug 1 into the function, I get 3 minus 6, which is negative 3. And then I evaluate the function at 3, and I get 27 minus 18, which is 9. So now we're just focused on these 3 numbers, right? Highest value is your absolute max, lowest y value is your absolute min. And the answer is going to be the y values, okay? Answers are the y values. Not order pairs, not x values, the y values. Okay, question? Okay, give you guys a moment. All right, so that's extreme value theorem. Any questions there? Okay, the next theorem up is Rolle's theorem. So we'll do I'll go through that concept or that theorem, and then we'll look at an example. All right, so here's Rolle's theorem. So the purpose of Rolle's theorem is to guarantee a location on the graph where there's a slope of 0. Okay, we're looking for a slope of 0. We don't really care whether that slope 0 is a max or min or neither. We're just looking for slope zeros. But we want the slope 0 to live between the interval or live between the endpoints. Now, if we're trying to guarantee that a location exists where there's a slope 0 without looking at the graph, we're going to be relying on these conditions and statements to help us guarantee that, that conclusion. So just like with extreme value theorem, we first have to establish that our function is continuous, okay, on the closed interval. So no vertical asymptotes, no holes, or rather, you can have asymptotes and holes as long as they don't interfere with the interval. But there's another condition that's required because extreme value theorem, we're just trying to find max and mins, right? We don't really care if the graph is smooth everywhere. But with Rolle's theorem, because we're trying to guarantee a slope of 0, we have to first ensure that everything we're dealing with in the interval is safe in terms of that the slope is available to be found, right? So we can't have any sharp turns if we want to apply Rolle's theorem. So we need the function to be differentiable. So our function needs to be differentiable on the open interval. Usually, you don't have to worry about this statement, okay? If it passes the continuity statement, it'll most likely pass a differentiable statement. The only thing I would say that where we may run into some issues, if you have these radicals where you have odd roots, like actually 5/3 is not going to be an issue. Yeah, it's basically any odd roots where the numerator is lower. So let me readjust this one. So more like, it's very specific, right? These types of functions here. So maybe like 3/5. Yeah, these odd roots, they kind of sometimes produce graphs that look like this, and we have points that are where the graph may not be smooth all the way through. Okay, but for the most part, this is not something you have to worry about. Just have to be aware that this is a condition to guarantee that we need a smooth curve, a smooth all the way through for our graph between the endpoints. There's a third condition, and that is the endpoints have to share the same y value. Okay, we're trying to guarantee a slope 0, so we need to be able to ensure that the graph is directly across from each other. Because you can imagine that a graph where 2 points are directly across from each other, you're able to draw a horizontal line. And that horizontal line represents the slope 0 that we're trying to locate. So if there's a slope 0 between the endpoints, there's a guarantee that the graph must have a slope 0 in between. And that's what we're looking for. We're looking for that slope 0. So once we have all three conditions squared away, we can then start looking for our location where the slope is 0. So we find the derivative, we set it equal to 0, and we solve for x. And when we solve for x, we want to make sure that whatever, we're guaranteed at least one solution. But if there's multiple solutions, we may have to be a little suspicious because we need every critical point to land between the endpoints. If it lands outside the endpoint, we have to remove it. All right, so let's do an example here. Our function is 2x cubed minus 6x on the closed interval from 0 to √3. And we want to see if we can apply Rolle's theorem for this function. Okay, so the first thing I notice is I've got a nice polynomial. So continuity, differentiability is not going to be an issue. We know those two first conditions are good to go. Remember, continuity is with brackets. Differentiability is with parentheses. Okay, now we're ready for our third condition. Our third condition is plugging the endpoints into the function and seeing if they are equal. Are they going to be the same y value? So we're going to find f of 0. So 0 into the function, I get 0 minus 0, which is 0. Okay, plug root 3 into the function. I get 2 root 3 cubed minus 6 root 3. This ends up being 6 root 3 minus 6 root 3, which is 0. These are equivalent. Our third condition is good to go. We know that there must be a slope 0 that we can guarantee. Okay, so all up to this point, we're just making sure that our conditions are met. So now we can move on to our calculation, right? We're going to find the derivative, set equal to 0, and that will help us find that location. Okay, so f prime, we go through power rule. Set the derivative equal to 0, solve for x. And as a reminder, we only set the numerator of the derivative equal to 0. I know that in this case, there's no denominator to worry about, so it's kind of a moot point. But if there were a denominator, we don't look in the denominator. And the reason why is because if we set the denominator equal to 0, then what we're getting back in return is a potential location where slope is undefined. But we don't want slope undefined. We want slope 0. And also, we've already confirmed that there's no place of slope undefined, so we never have to look in the denominator, just the numerator. Okay, so we find the derivative, factor, solve for x, and I get two x values, right? I get x equals 1 and x equals negative 1. Okay, but do we keep both values? What do we have to check once we have our potential solutions? Yeah, within the interval. So negative 1 is out. Now, if you realize that all of your critical points end up outside the interval, then there's a problem, right? This is a guarantee. Once you get past the third condition, we must be able to find, we're guaranteed to find at least one location. So if you find that all your values are outside the interval, that means something didn't go quite right in your calculation. You got to go back and look. There must be one solution that is that will pass the test. Okay. I just want to show you what we achieved here. So this is what the graph looks like. We found that f of 0 and f of 0 root 3 is equal to 0. So once we're at this point, we knew that without looking at the graph that there must be a point where there's a slope 0. So what happened was there was actually 2 points where there's slope 0. But because this one is outside the interval, we're only the derivative process is only giving us a location where the slope is 0 between the endpoints, and it was able to find it at negative 1. Sorry, at positive 1. Or positive 1 for the x value. This is the x value, not the y value. Okay, any questions with Rolle's theorem? All right, let's look at mean value theorem. So mean value theorem is similar to Rolle's theorem. We're also trying to guarantee a specific slope. Our conditions are going to be very similar as well. But mean value theorem is not as restrictive as Rolle's theorem. Rolle's theorem is only looking for one thing, right? It's only looking for slope 0. With mean value theorem, it's more flexible. It just wants to find whatever slope exists between the endpoints. But once we find that endpoint slope or slope between the endpoints, then that is what we're trying to guarantee. So for instance, let's say we had a graph that looked like this, right? Smooth curve, endpoints are A and B, and we take the time to find the slope between the endpoints, and that slope ends up being 1/2 or 3 or 5. Whatever that number is, whatever that slope is now a guarantee somewhere between the graph. So if there's a slope of 5, I know that I can find a location where there's also a slope of 5. Okay, and that's what we're trying to do. We're trying to find that location. So conditions look very similar initially. It needs to be continuous on the closed interval, so no vertical asymptotes, no holes. It needs to be differentiable, it needs to be a smooth curve. And then there's no third condition. We don't have to verify that the endpoints are the same y value because we're not trying to guarantee slope 0. So all we need to do is we have to go through this process of fulfilling this formula. But there's a specific way that I want you guys to approach this formula. The first thing we're going to do is we're going to just focus our attention on the right side of the formula. Okay, let's not find the derivative yet. So what this is saying is, find the slope between the endpoints, f of b minus f of a over b minus a. So what we're going to do is we're going to take those x values that they give us, plug them both into the function, find their y values, and then find their slope. Let's say that slope is 5. Okay. Then we can take the time to find the derivative. Okay. And once you find the derivative, you can set that slope value of 5 equal to the derivative. And when you solve for x, again, we only care about what's inside the interval. When we solve for x, we find a location where that specific steepness on the graph is existing. Okay, so let's do a practice problem with that. Mean value theorem example. The first thing I notice is it's a polynomial, so no issues with our graph, no vertical asymptotes, no holes, no sharp turns. So I know that my first two conditions are good to go. No issues with continuity, no issues with differentiability. Okay, so now we're going to be putting in the work to figure out the parts of our formula. Okay, again, ignore the derivative process. That's not the first thing we want to do. We want to take those endpoints, plug into the function, so we can gather this information. We want to gather information about endpoints so we can find the slope. Okay, so we'll find f of -1, we'll find f of 2, and see where that takes us. Right? So -1 into the function, I get -1 plus 1 minus 1, which is -1. Okay? I plug 2 into the function. I get 8 minus 2 minus 1, which is 5. So we have our ordered pairs, right? Now we can focus our attention on trying to find the slope between those endpoints. So change in y over change in x. There's our slope. Questions so far? Okay, so this process is done, right? We found the slope. Now we can turn our attention to the derivative. So we'll find f prime, power rule, 3x squared minus 1. Now, when you find the derivative, we're going to have to make sure that we involve the 2 somehow, right? We're basically asking the derivative function to give us a location for a very specific slope. So our next step is to set the 2 equal to the derivative. Make sure that you don't put the 2 in for the x, because the 2 doesn't represent location, right? The 2 represents slope. So we got to put 2 into the appropriate location for slope information. Okay, so we set 2 equal to the derivative. Solve for x, so add 1 to both sides. Divide both sides by 3. I get plus or minus 1. So I have 2 locations where there's a slope of 2. But again, we got to go back to our interval, right? We only keep what's between the interval. So this is a subtle point here, but -1 is not good enough. I know -1 is sitting at the endpoint, but our C value must be between the endpoints. Endpoint alone is outside the interval. So we only have one solution, one location where there's a slope of 2 between these 2 endpoints, and that is when C is equal to 1. I just want to show you visually what we achieved here. So this is what the graph looks like. Okay, we plugged -1 and 2 into the function. We found those endpoints. We found that the slope between those 2 endpoints was 2. So now, after we found that the fact that this slope of 2 is 2, then we went searching using the derivative to help us find locations where a slope of 2 occurs. So we found a location at 1, and there's also a location at -1. But because -1 is outside the interval, we only hold on to our C value of 1, because that's the only place where we're experiencing a slope of 2 between these 2 endpoints. All right, any questions? Next up, so I've gone through each of the theorems, just want to kind of review through those theorems, make sure it's fresh in your mind. You'll expect that. You can expect to see those on the exam. Next up, I want to go over particle motion. So let's do some particle motion. Yes. Yeah, MVT, yeah, mean value theorem. Oh, IVT. IVT, is just finding guaranteeing a value. It doesn't involve calculus. I'm not going to put it on this exam. Yeah, so IVT is just, can I guarantee a value? I plug in the endpoints, make sure an endpoint is above and below the target, and then we can guarantee that value in between. But I'm going to leave it out of this exam. All right, this is from packet 1, but I kind of adapted it just for this example. So let's just work through this example. Now, particle motion is where we have a position, velocity, acceleration. But that relationship is going to be the same as a function f prime and f double prime. Okay. But a lot of times these, we kind of think about this as a particle moving along the x-axis. So let's say a particle is moving along the x-axis, and the position is given with this function. T is defined for all real numbers. So we're going to do 4 things here. We're going to find the velocity, which is just the derivative. We're going to find the intervals where the object is moving left or right. So to determine that, we're going to create a velocity sign line. So we'll find the velocity, set velocity equal to 0, find the critical points, populate it, test values on either side. Positive means moving right, negative means moving left. Okay. Next up, we're going to find acceleration, which is really the second derivative. And then part D is the speed increasing or decreasing at t equals 1. What we're going to do here is we're going to compare signs. Between velocity and acceleration. Okay, so let's go through each of these parts. So first up, find velocity. So velocity is just the derivative. So just go through power rule. So velocity function is just 3t squared minus 12t plus 12. Part B, we want to find intervals moving left or right. So we're going to create our velocity function. So to create our velocity function, we're going to set velocity equal to 0. Find the critical point there. I'm going to go ahead and begin to start factoring. So I factor out to 3. The rest is also factorable. Multiplies to be 4, adds it to be negative 4. Okay, we solve for t, we get t is equal to 2. So that's the only critical point that's going to go onto our velocity sign line. Okay, so I'm going to place velocity 2 onto my velocity function, onto my velocity sign line. And now I'm just going to be choosing values on either side of 2. So I want to know how the object is behaving to the left of 2 and then to the right of 2. So I'll take 1, put it into my velocity function, and see what that gives me. Is it giving me a positive or a negative value? So if I plug 1 in for t, I get 1 minus 2 times 1 minus 2. That's negative times negative, which is positive. If I plug 3 into velocity, I get 3 minus 2 times 3 minus 2. It's also positive. So this particle is pretty much always moving to the right, except for one moment in time when it stopped. So we're not going to be able to make any statements about interval moving left. Our only statement is going to be where object is moving to the right. Okay. And our reasoning is moving to the right in these 2 intervals because velocity is greater than 0. Okay, question so far with part B. Okay, part C, find the acceleration. So to find acceleration, we're going to have to find the derivative once again from velocity down to acceleration, but just go through power rule. So I get 6t minus 12. Right. Part D, is the speed increasing or decreasing at t equals 1? And our strategy there is we're going to be finding the velocity at 1, finding acceleration at 1, and compare their signs, right? If their signs are different, then we're expecting decreasing speed. If their signs are the same, then increasing speed. So either both positive or both negative would fall under increasing speed. Okay, but for this problem here, velocity is 3, acceleration is equal to -6. One's positive, the other is negative, so therefore speed is decreasing at t equals 1. I just want to kind of give you an overview of particle motion so you can kind of see the big picture and see the process for a lot of these types of problems. Okay, any questions? Okay, let's do one more. And this one, we're going to find intervals of concave up and concave down. Okay, so this kind of falls under the category of curve sketching. Okay, this is number 52 from packet number 1. Let's say we have a function that's x minus 1 over x plus 3. We want to find interval where the function is concave up. So to do that, we're going to have to work our way all the way down to the second derivative function, and then we have to create its sign line. So that means we have to find the critical points from f double prime, create our sign line, test intervals. Positive would represent concave up, negative would represent concave down. All right. But to find to work our way down to the second derivative, we first have to find f prime, right? We first have to find the first derivative. So how do I get from f to f prime looking at how this problem is set up? We got to use what? To find the derivative. Quotient rule, yeah. Go through quotient rule. So f prime g minus f g prime all over g squared. So spend a minute, see if you're able to find the derivative and get that cleaned up. Because once you find the derivative, we gotta get it ready for the next derivative, right? Because we're only halfway there. Okay, let's see what you guys got. F prime g minus f g prime all over g squared. Careful, right? We've got to distribute that negative through. This negative has to distribute to both terms that comes after it. And I got it all the way down to 4 over x plus 3 squared. Okay, so that's my first derivative. We don't find critical points here. If we find critical points here, then we're gathering information about max and mins and increase, decrease. But that's not what the problem is asking for. So we have to work our way down to the second derivative. But I'm looking at how this problem is set up, and I don't see a variable in the numerator, which means that I can avoid quotient rule. I mean, quotient rule is fine, but anytime I can avoid quotient rule, I'm going to try to avoid it. So I'm going to bring that x plus 3 squared up, and that way I just have to rely on chain rule instead. I prefer chain rule over quotient rule, if possible. Now, if there was a variable up here, then yeah, then I would just go through quotient rule. But I'm going to rewrite it first. I'm going to get that rewritten as 4x plus 3 to the negative 2. And then when I find the derivative here, I can just go through chain rule and think of it as outside, inside. Right? My outside is the 4 parentheses to the negative 2. My inside is the x plus 3. We're just going to take turns with each of their derivatives. Okay, so outside's derivative is negative 8 parentheses to the negative 3. Inside's derivative is 1. So there's our f double prime. Okay, I'm going to do a little bit of cleanup. Once I have my second derivative all nice and cleaned up, I'm going to start looking for critical points, right? Because those critical points is what we want to populate our sign line with. Here, we look in the numerator and denominator, right? This is not Rolle's theorem where we're trying to guarantee slope 0. We just want to find any critical point that we can find. So numerator, nothing comes of it, right? Negative 8 doesn't equal to 0. But if I set x plus 3 equal to 0, I get x equals negative 3. Now, to let you know, negative 3 is actually a vertical asymptote, but we still want to put it onto our sign line because it helps separate our intervals of concave up and concave down. So negative 3 is going to go onto my second derivative sign line. And I'm going to choose points on either side of negative 3. Right? I'll choose negative 4 on the left. I'll choose 0 on the right. And we want to test concavity, so these values will get plugged into the second derivative. And we just want to, we only care about whether it's positive or negative result. So negative 4 plugs in for x. Negative 4 plus 3 is negative. Negative cubed is negative, so negative over negative is positive. So this interval is concave up. Positive represents concave up. Okay. Plug 0 into the second derivative, I get negative over a positive. That's negative, so concave down. So the problem is asking for intervals of concave up. So I'm just going to look at this first interval here, right? From negative infinity to negative 3. When you write your intervals, right, you don't include those test points. Those test points is just to get that sign to show up, but after that, we're just going to ignore it, right? It's not part of our interval statement. Right? So from negative infinity to negative 3 is concave up, and our reasoning is because f double prime is greater than 0. Okay, any questions? Okay, so that's the last thing I want to do today. On Monday, I think we've hit a lot of these topics already. It's just the last few remaining. So on Monday, I want to review through the new derivative rules that we've seen recently from Chapter 5, mainly Chapter 5 material. Finding derivative of logs, so knowing how to expand before you find the derivative. Log differentiation, we'll practice one of those problems. Finding derivative of inverse at a point, this is where you guess and check. Find the x value. After that, derivative, slope, and then flip that slope value. A couple of housekeeping items here. Help sessions. So I'll do help sessions morning and afternoons, Teams as well as in person. will be recorded. So this afternoon, I will focus on problems from packet 1. So I'm just going to pick out problems from packet 1, or if you have questions from packet 1, I can go over them. On Monday, I'm going to pick out problems from packet 2. And then Tuesday, Wednesday, Thursday, morning and afternoon, I'll pick out problems from packet 3. Okay, so most likely you guys are only going to attend on the days where your exam is or the day before, which is fine, but I want to make those available to you. Okay, any questions? Okay. Yeah, I got an email from Mr. Jones, Principal Jones sent out an email yesterday, kind of giving us a preview as to what's going to happen next semester. Did you guys hear about it? That I think might be going to a block schedule. So I may just see you guys like every other day, and you're only going to have like, 3 periods a day or something like that. But then it's going to be extended like 90 minutes. So I don't know how that's going to look. That's going to be quite an adjustment in the middle of the school year too. So that's all I know right now. Guess I'll find out more when they share with us. So, all right. If you're on Teams, have a great day. Have a great weekend. I'll see you guys Monday.